Hey everyone, welcome to exponential models, exponential and logarithmic models. This is Mr. Bennett, and we're going to be looking at one example today relating to radioactive decay. It's a big example here. So we did this in a previous video. The radioactive isotope of potassium 42 is vital to the diagnosis of brain tumors. It has a half-life of 12.36 hours. Part A, determine the exponential decay model that represents the mass of the potassium 42. If B, if 500 milligrams of this potassium are taken, how many milligrams remain after 2 days, 48 hours, and how long will it take for the original sample to decay to a mass of 5 milligrams? So we're going to go ahead and first look at Part A, and it wants the exponential model. So the first thing that we need to do is write the relationship between rate of decay and half-life. So that is going to actually equal R is equal to the natural log of 2 over H. Okay, we need to find our R value, and I'll show you why in a second. And so when we plug in H is equal to 12.36 and simplify, we get approximately 0.056 is equal to R. Okay, so the exponential model for this, okay, the mass is going to equal to the initial amount times e to the negative 0.056t, okay? And that's going to be the model for potassium. Now, part B is a little bit easier, so we have part A all taken care of. So part B, if we cursor down, move this down a little bit. If 500 milligrams of potassium 42 are taken, how many milligrams remain after 48 hours? So we know that the initial amount here is going to be equal to 500. That's what we take. E to the negative 0.56 t is going to be 48 hours. Now we can go ahead and just plug this into our calculator, okay, to see what that total is going to be. So we can go ahead and do 500 times e to the negative 0.056 times 48. Okay, that looks good, and it's going to be approximately 34.008. So how much is going to be left after 48 hours? Approximately 34.008, and that's milligrams. That's going to be left in this system. Okay? Now let's look at part C here. Part C, how long is it going to take for the original sample to decay to a mass of 5 grams, or milligrams, excuse me. So in part C, m is going to equal 5, and m sub 0 is going to equal 500. Okay, so now it's just applying what we know to our formula. So the formula is m is going to equal m sub 0 e to the negative 0.056 t, and now it's a matter of substitution. You have 5 equals 500 times e to the negative 0.056 t. We want to find t, so it's a matter of taking the natural log and dividing here. So we're going to have 500, or excuse me, 5 over 500 equals e to the negative 0.056 t. You take the natural log here of both sides. There's 5 over 500 equals the natural log of e to the negative 0.056 t. Okay, that's going to help us simplify, and we're going to get that t out front like we like so we can solve for it. Okay, so the natural log and the e are inverses, so you get negative 0.056 t. You divide each side by negative 0.056, and so we're going to get approximately here, let's look. Okay, you're going to have the natural log of 5 over 500, which could be simplified to 1 over 100. That's okay. Okay, so we have that, and then we're going to divide that. Oops, it's a negative divided by negative 0.056 to get to t. It looks like 82.24. It's approximately 82.24 is going to be T. So that's going to take about 82 hours, not 82 years if I said that, I don't know if I did, for the substance to decay to a mass of 5 milligrams. So that's just another example of radioactive decay, or exponential decay, excuse me, and another example of exponential logarithm models. If you guys have any questions or comments, you can go ahead and type them below. We'll see you next time.